Okay, good morning, everyone. Okay, welcome to the calculus class. It's Monday morning, and okay, let's see what we have today. So, so we will consider the last section of chapter 4. So, okay, and then let me first finish this section. Okay, so in section 9, we are considering the antiderivatives. See. Okay, so we want to consider the antiderivative of a function. So if we have a function, say the uppercase f, and if we have a lowercase f, and if these two are related by this. In other words, when I differentiate this uppercase f, if I get this lowercase f, then at this point, previously we called this lowercase f as the derivative of the uppercase f, right? So this lowercase f is the derivative of uppercase f, right? Now, given this a lowercase f, we want to call this uppercase f somehow. And at that point, we use this term. This uppercase f will be called an antiderivative of a lowercase f. Okay, so if lowercase f is the derivative of certain function uppercase f, then at this point, please remember this uppercase f is called the antiderivative of this lowercase f. So in terms of the viewpoint, we have different name. So given uppercase f, lowercase f is the derivative. And given lowercase f, this uppercase f is called an antiderivative. Now, given uppercase f, you have only one derivative. In other words, given uppercase f, this lowercase f is uniquely determined, right? However, given lowercase f, uppercase f is not uniquely determined, right? I mean, so please remember, given, say, uppercase f, say sine x, then the derivative is unique and you get just the cosine x. But given lowercase f, you may have multiple antiderivatives. Say sine x is definitely one of an antiderivative. If you differentiate sine x, you get cosine x, right? But what if I differentiate sine x plus 1 with respect to x? Then you also get cosine x because the derivative of 1 is 0. So we have, given lowercase f, you may have many antiderivatives. So antiderivative is not unique. So here is another example. If I consider lowercase f with, say, x squared, then when I differentiate 1/3 of x cubed, you get x squared. But as I said, that's not the only one. If you differentiate, say, 1/3 of x cubed plus 100, its derivative is also x squared. So these two functions, uppercase F and uppercase G are both antiderivatives of F. And when you look at this G function, you may expect that, okay, if I have any constant addition to uppercase F, then the derivative of such a function will be always lowercase f, right? So, so antiderivatives are not unique. Actually, you may add any constant, and this addition of constants does not change the derivatives, right? So, so we have a one very simple theorem. So if uppercase F is one of the antiderivatives of lowercase f function, then the most general antiderivative of f is this uppercase f plus any constant. So going back to the function x squared, we see that the general antiderivative of f is 1/3 of x cubed plus a c. Okay? So by assigning many different values to the constant, you see many different antiderivatives for x squared. Now, now, if you fix one x value, f prime of each of these functions is x squared, right? Now, what is f prime? What is the derivative? Derivative represents the instantaneous rate of change, or graphically, it represents the slope of the tangent line. Now, if I fix the x value, as you can see, the slopes of the tangent lines of all these functions are the same, which means they have the same derivatives. In other words, they have the same rate of change or the same slopes. I mean, the tangent lines, okay, will have the same slopes. So let us consider the following example. Find the most general antiderivative of each of the following functions. So as I said, in case of sine x, if you differentiate cosine x, okay, at this point, some people make a mistake. If I differentiate cosine x, you get negative sine. So to get the sine x, I need to differentiate negative cosine. So if you differentiate negative cosine, you get the sine x, right? But that's not the only one. When you add any constant to negative cosine x, you get sine x. So the most general antiderivative will be negative cosine x plus c. And we use this c in general in calculus. Okay, in almost every class around the world, they use this capital C to express some general antiderivative. I mean, okay. So given uppercase F, here is uppercase F, and that is one of the antiderivatives. And if I add the constant to c, then depending on the value of c, you will have very different antiderivatives. Okay. Now, how about 1 over x? Oh, actually, let me consider this c first. What if x to the n? What do I get? Okay, if you remember that when I differentiate x to the n, you get n times x to the m minus 1. So the power of x decreases by 1. Now, I need to have this exponent n after differentiation. So before the differentiation, I must have the n plus first power. But when I differentiate x to the n plus 1, you will multiply n plus 1 to the x to the n. So in order to have the coefficient 1 in front of x to the n, I need some cancellation of this n plus 1. In other words, before the differentiation, I need the n plus first power of x, and then after differentiation, this n plus 1 must be cancelled. So probably I need 1 over n plus 1 so that once I differentiate this function, you get x to the n. So this is one of the antiderivatives. So to get the general antiderivative, I need to add c. Okay. Okay, let me first complete this section because some students got late, and then let me talk about the midterm. Okay, so please wait. Okay, I will talk about the midterm in an after I finish this section. So please wait. Okay, so this will be the general antiderivative of x to the n. Okay, now let me go back to the 1 over x function. So this one is quite confusing. Okay, first of all, if you see this 1 over x, and if you remember the logarithmic function, okay, the log x, once differentiated, you get 1 over x. So you may say, okay, given this 1 over x, the logarithmic function, natural logarithmic function is an antiderivative. So if you claim that, okay, this is an antiderivative, so the general antiderivative of 1 of x must be log x plus constant c. Then this is half correct. This is not perfect because because when I consider 1 over x, what is the domain of this function? Domain is this 1 over x is well defined as long as your x is not 0. So from the real line, if I exclude 0 from the real line, then for any x value on that interval, my 1 over x is well defined. However, if I consider log x or log x plus c, what is the domain of this uppercase f? Then this function is defined only when x is non-negative. So its domain is only positive positive values. So this uppercase f will be an antiderivative of 1 over x if I consider only positive x. Then how about this negative x? So if you write down log x plus c, then that is half correct. And for if this were the actual exam problem, then you would get only some partial credit because you didn't answer, you didn't find the antiderivative for these negative x values. Okay. Now, now if I consider, so, so to consider this negative x value, let us consider the derivative of log, okay, in case of log absolute value of x, or the derivative of this guy, then for positive x, log absolute value of x is just the log x, so that its derivative will be 1 over x. However, for negative x, absolute value of x is negative x. So log absolute value of x will be log negative x. And for this negative x doesn't cause any problem because we are considering the negative x value. So with negative sign in front, negative x will be positive. So natural log of negative x is well defined. Now, given this expression, if I differentiate this guy, you see the composite of two functions. So log negative x, when it is differentiated with respect to x, I need to apply the chain rule. You first differentiate this, you need to differentiate the outer function, which is natural logarithmic function. So you get 1 over negative x. That is the derivative of the outer function evaluated at negative x, the inner function. Now, you need to multiply the derivative of the inner function. So if I differentiate negative x with respect to x, you get negative 1. So negative sign will cancel out and you get just 1 over x. Okay, so this expression shows that for negative x, if I differentiate log of the absolute value of x, you get 1 over x. So that answers this negative part of the interval. Okay. So what is the answer? What is the correct answer? Instead of this log of x without the absolute value sign, the correct antiderivative will be log absolute value of x plus constant to get the general antiderivatives. So So please remember that, okay, when I give you any function, say 1 over x, your antiderivative must have the same domain as the function given. Okay, so this log of just x without the absolute value sign is not complete answer. Okay, we need to put the absolute value sign before we take the logarithmic function. So this is the one of the antiderivatives. And if I add the c, you get the general antiderivatives. Okay. So yeah. So that's, oh, okay. Now, one comment. So as I said, I need to add c for the general antiderivatives. So let me go back to my expression. So this 1 over x is an antiderivative. I'm sorry, the log x is one of the antiderivatives. So for positive x, so I need to add certain constant to that antiderivative to get general antiderivative. And for negative sign, I have log of negative x. That is an antiderivative. And I need to add certain constant to get general antiderivatives. Now, so I have two constants, one constant for positive x and one constant for negative x. So, so I have one constant for positive x and another constant for negative x. So this is the correct answer, correct expression for the answer. Okay? That is correct answer, perfect answer. But sometimes if we read a textbook or paper, then so everyone understands as long as they know the concept of antiderivative. As long as they know these antiderivatives, they know that okay, I need two constants. And actually the constant for positive x doesn't have to be the same as the constant for negative x. Okay. So so okay, then so I need two constants. But since this is so trivial, everyone knows that okay, everyone knows that okay, there will be two different constants for different intervals because these two intervals are not connected. You have disjoint intervals, which is split at zero, right? So, so I mean, given this log x and negative log x, so log x and then negative x, if I add, say, certain constant and possibly different constants, then this is still an antiderivative of 1 over x, right? You don't have to add the same constants to the positive part and negative part. So you need to write down C1 and C2 to express the situation, okay? But since this fact is so trivial, okay, so if anyone understanding the concept of antiderivative understands this situation, so people usually, even though they require two distinct constants, they use just this single expression, okay? But even though you use this single constant, okay, that notation implies that you might need two distinct constants for different distinct intervals. Okay, so people sometimes use this expression instead of this, but you need to understand that this single expression implies this. Okay, so so when you read some, say, engineering math or engineering calculus or some other textbooks, this should be the expressions, common expressions, okay, shared by the people here. Okay, and so here is some formula, some simple table. Okay, and this table might be needed for your exam. So if I have this function, so suppose that given f uppercase f, if I differentiate, you get lowercase f. And given this uppercase g, suppose that this when the differentiated, you get say lowercase g. In that case, for these functions, they are antiderivatives. Okay? Of course, the general antiderivatives are defined by adding constants, but this addition of constant is so trivial. This it is just okay, it is not shown in this table because it is trivial. Given x to the n, you need to add this function to get x to the n. So this is the functions on the right are just one particular antiderivatives. To get the general antiderivatives, you need to add a constant. Okay, so you need, for the general antiderivatives, you need to add a constant. 1 of x, you need to consider, you need to differentiate log absolute value of x. If you differentiate e to the x, you get e to the x. If you differentiate b to the x, you get b to the x times ln(b). So in order to have b to the x, you first need to divide b to the x by ln(b) so that after differentiation, you have only b to the x. If you differentiate sine, you get cosine. So an antiderivative of cosine is just a sine, not negative sine. And in case of sine, you need to differentiate negative cosine. And to get secant squared, you need to differentiate tangent. If you differentiate secant x, you get secant x times tangent x. Or if you differentiate these functions, you get these. Or if you differentiate these hyperbolic functions, you get these, and so on. Right? So these are some simple situations, simple examples of antiderivatives. And please be familiar with this formula. Okay, okay, and okay, we need to cover, okay, as you can see, 4 more sections. Section 2 up to section 5 will be considered. So since some students are asking, so regarding the midterm, nothing is changed. What did I tell you on the first day? Okay, actually, if you do not remember what I told you, you can check the YouTube video which I uploaded, and you can just download the updated syllabus which you can easily download from the LMS website. The exam will be given on April 22nd, Wednesday, from 9 to 10:15, and we have the exam, the in-person, not online exam. You need to come Hana Science Hall, room B214, basement. Room 214, not second floor. Okay? So B for the basement and room 214 in the basement. Please do not go to the second floor. You need to come to the basement. Okay? Room 214. And the exam will start at exactly 9 and it will end at 10:15. Okay? And okay. You calculator, oops, is allowed, but no other electric devices, such as laptop, tablets, cell phones. Those are not allowed, which means if you have only, say, if your calculator is available only at the cell phone, that is not allowed. Okay, the calculator of the tablet, not allowed. Okay, so when I say the calculator, just actual calculator. Okay, not the calculator app. Okay, in a tablet, laptop, or cell phone, those are not allowed. I don't think calculator is needed myself, but if you feel comfortable with some calculator, you can bring it with you, but it is not needed. It is not a, okay. So if you do not have an actual calculator, okay, no other device is allowed. Now, and what did I tell you? Okay, on the first day. Okay. Mm, oh, okay. And one cheat sheet on A4 page is allowed, but it must be one-sided only. If your cheat sheet has two sides, I mean, if you write down on both sides of the paper, it will be confiscated. You cannot use it. Okay. And it all the information on your paper must be handwritten only. Okay. So if you make any photocopy or reduction of the photocopy, those are not allowed. Okay. So if you write down something, okay, that is allowed. If you just copy it, or if you reduce, or if you just copy some image, okay, so if you take some copied version from your PDF file, that is not allowed. Okay. So if any part, any part of the cheat sheet has some image from the textbook or slide or from certain outside material, that cheat sheet is not allowed in the exam. Okay. So as I said, all the information on the cheat sheet must be handwritten only, and the paper must be one-sided. Then you can bring this cheat sheet with you with the exam. All other devices, electric devices, are not allowed. No other devices are allowed. Okay, what is the question? Understood. Okay, so I will probably complete the chapter 5 this week, I think, or at most, and possibly, yeah, possibly this week. Okay. So once I finish this, I will go over some sample problems so that all the information can be shared, I mean, fairly and shared. Okay. So let me show some examples. Okay. Probably on next Monday before the exam. So on 20th, I will show some sample problems. And what else? Yeah, so these are the information of the exam. And regarding the format, I mean, some students are asking the format of the problems. So I will show the sample problems, as I said. Okay. And the formats, I mean, will be explained on that day, on Monday. So please wait. And I got a couple of emails regarding the sample problems. So, oops. The You can please consider the only sections we covered in class will be considered. Only sections in chapter 1 through 5 we covered in class. Those will be considered. If I skip certain section, you can skip that section as well. Okay? So only sections we considered. Say we didn't cover section 7, 8, 9 in chapter 3, right? I didn't consider section 5, 6, 7, 8 in chapter 4. So you can skip those sections. And if you have a textbook, please check the exercise problems. Most problems will be very similar to the exercise problems. And usually I prefer just first one third. Okay. You can just consider, say, if certain section consists of, say, 90 problems, then you can just look at first 30 problems only. Okay. So first one third of each exercise problems will be sample types of the exam. Okay. I mentioned the coverage, right? So please check my slides. If you missed it, please check the video lectures again. Okay. So these are the coverage of the exam. So that's the coverage and that's the information about all the information you need for the exam. Okay, okay, then let me go back to the lecture notes and let us consider chapter 5. Okay. Sometimes, sometimes you see the value of certain function at certain point. Okay, so here's the situation actually. Suppose that we have x1, x2, x3 up to xn, and the xn minus xn minus 1, or if delta x denotes xi minus xi minus 1, so if that is fixed for all I values, so that means x2 minus x1 is the same as x3 minus x2, which is the same as x4 minus x3, and so on. In that case, if I have certain function, and if I choose any point, say x1 star between x1 and x2, and if I choose any point, say x2 star between x2 and x3, and so on, and if you evaluate your function at x1 star, x2 star, and so on, then that means at x1 star, your function has a certain value. When I multiply delta x, you get the area of this red rectangle. And then if I multiply x2 star with delta x, then that will represent the area of this green rectangle. So if I compute each term, and then if I add them, okay, if I do this calculation, and then if I increase the value of n, so here delta x denotes xn minus x1 divided by n, oh, n minus 1. So that is the step size. And if I increase the value of n, then that means my rectangles have smaller and smaller width, right? So eventually, if I do this calculation, what you obtained is the area of the region below this graph between x1 and xn. So if I compute this calculation, then that will give you the area of the region governed by the graph of y equals f of x between x1 and xn. Okay. So from this, we want to give certain meaning, okay, to that expression. So here is the definition of the definite integral. So given some interval from a to b, and suppose that I have the graph of y equals f of x. Between these 2 points a and b, let me split this interval into many small bins of the same size. So let me define delta x by b minus a over n. And then let me call xa by x naught. Then next points are called x1, x2, x3 in that order. Okay. And then between any points between x0 and x1, you choose any arbitrary point, say x1 star. Between x1 and x2, you select an arbitrary point, say x2 star. At each x1 star or x2 star, you evaluate your function. Okay, so at each point xi star, if I evaluate my function, and then I multiply delta x. And then I take the summation of this, and then I will reduce the step size. In other words, I will increase the value of n so that your delta x becomes smaller and smaller. Now, this is a limit of a certain mathematical expression, and that expression may not have the limit. But if this limit exists, so if this limit exists, then we express that limit using the symbol of this lengthy S-shaped symbol with f of x dx, and then this lower limit a and upper limit b are used as this subscript and superscript of this S-shaped symbol. So if this limit exists, then that limit will be denoted by this notation, by this symbol. Okay, so let me go back to this. So given my function f, I define delta x by b minus a over n, and I split the interval into small bins, as I said, and a will be denoted by x naught and b will be denoted by xn, and then I will split this interval into n pieces. And on each interval, I will choose on arbitrary numbers. So they are called sample points, which means they are some arbitrary points between x naught, x. So x1 star is an arbitrary point between x naught and x1, and x2 star is an arbitrary point between x1 and x2, and so on. So xi star is an arbitrary point between xi minus 1 and xi. This xi star may be xi minus 1, it may be xi, or it may be the center of the interval. Okay, so between xi minus 1 and xi, you will choose an arbitrary point, and that will be denoted by xi star. Okay, so you select those n numbers, you evaluate your function there, multiply delta x, take the summation, and then you increase the value of n. If this limit exists, then we use this symbol to express the limit. Okay, so if that limit exists, then we use this symbol, and this symbol will be called the definite integral of f from a to b. That is the name of this symbol. Okay, and if this limit exists, then we say your function is integrable. Many functions are integrable in our calculus textbook. I mean, many functions you already know will be probably in many cases integrable, such as sine or cosine functions or some exponential functions. They are all integrable functions. We will see some non-integrable functions as well. So if this limit exists, okay, then we will say the function is integrable and the limit will be expressed by this symbol. And this symbol will be called the definite integral. So definite integral is a number, okay, representing this limit. At this point, this f, given this expression, given this notation, the f of x will be called the integrand of this definite integral. A and b are called limits of integration. In particular, a is called the lower limit, and b is called the upper limit. And at this point, dx is simply this is a symbol indicating that our function f is given as a function of x. In other words, the independent variable is x. That's what this dx implies. And the procedure of calculating an integral is called an integration. And as I said, the definite integral represents the limit value. So it will be some number. And in this definite integral, this x is just the name of an independent variable. Okay? There is no special meaning in x. I mean, you can simply replace this x with any other symbol. Say, x can be replaced by t or r or theta or s. Okay, it doesn't, okay, it can be replaced by any other symbol. Now, as I said, this definite integral is the limit of this summation, and this summation is called a Riemann sum of this function f. So the definite integral is the limit of a Riemann sum. If the limit exists. So I will use this concept a few times. So if if I have some expression like this, I mean, if I have a Riemann sum, then it's a limit. If the limit exists, then if the limit will be replaced by this definite integral. So please remember this. And as I said, what is the meaning graphically? Given this function f of x, on each interval, you choose an arbitrary point and you evaluate your function at that point and then multiply delta x. So the Riemann sum is representing, Riemann sum is just the sum of the areas of the approximating rectangles in figure 1. Then what will be the meaning of the definite integral? Well, the definite integral is the limit of the Riemann sum. And as you can see, the Riemann sum is just approximating the areas below the graph. So the definite integral as the limit, if you take the limit as the n goes to infinity, eventually this definite integral will represent the area of the region bounded by the graph of f of x and the x-axis and two vertical lines, x equals to a and x equals to b. Okay. Of course, that's the case when your f is non-negative. Then, what will be the meaning of the definite integral when your f is a negative valued? What happens if I have a negative valued f? So here is my f of x. Then what will be the meaning of this definite integral? Well, similarly to the positive case, if I split the interval into small pieces, and then if I evaluate my function at certain point, you will introduce a certain rectangle on each interval. right? And then if you so if so the what will be representing the Riemann sum? The Riemann sum approximates, oops, the negation of the area, okay, the area below between f of x and x-axis, right? So if you have certain this yellow region here, or so you have this region between the x-axis and the graph of f of x, right? But the area is always non-negative. And since Riemann sum just multiplies the function value with delta x, and delta x is positive and function values are all negative, so this Riemann sum is a negative valued. So Riemann sum for this negative f of x will be negative valued, and so that will approximate the negation of the area between f of x and x-axis. So what will be the limit case? What will be the limit situation? As n goes to infinity, as n goes to infinity, if your f of x is negative valued, then the integral, definite integral, will represent the negation of the area between the graph and the x-axis, right? So when your f is positive valued, you approximate, you get the area between of the region. For negative valued, you are considering the negation of the area. In other words, you are just so So here for positive side, you get the approximation of the area between A and, say, if this point is, say, C1, then the area of the region bounded by f of x and x-axis between A and C1, the area will be represented by the definite integration. So the integration of f from A to C1 will represent this area. If this point is C2, then the integration of f of x dx from C2 to B represents the area of the region. But if I integrate this function from C1 to C2, you get a negative value. So if I put negative sign, that will be the area of the region between C1 and C2. So integration of f from A to C1 represents the area of the region between A and C1, and this is the representing the area between C2 and B. But for negative value the function, if you integrate the function, you get the negation of the area. Okay, so that is the negation of the area of the region between C2 and C1 and C2. So, so if I combine all these, if I integrate my function from A to B, then probably this will combine all these three values, right? So for the interval between A and C1 and the interval between C2 and B, you get positive values representing the areas of two regions above the x-axis. But the integration between C1 and C2, you get the negative value. So what I get is the following. So if f takes both positive and negative values as in figure 3, then the Riemann sum is the sum of the areas of the rectangles that are above the x-axis and negatives of the areas of the rectangles that lie below the x-axis. Okay, so if I take the limit, then the integration will be representing the area of the regions above the x-axis. So A1 represents the area of the region in blue. Okay, so this is the area of the region above the x-axis which are in blue. Okay, and A2 is the area of the region below the x-axis and the above the graph of f. So that is the area in orange. Then the definite integral will give you only the difference between these two. In other words, it will give you the net area between the graph of the function and x-axis. Okay, and let me skip this one. So in theorem 3, we are not going to prove that, but if your function is continuous on the closed interval between a and b, or even if that function is not continuous, but if it has only finitely many jump discontinuities, okay, then your function will be integrable. What is a jump discontinuity? Please remember, finite number of jump discontinuity or removable discontinuities. Okay, then your function is integrable and the definite integral exists. Now, what is a removable discontinuity? If your function is continuous except a certain point and your function is not defined there, or for or your function is defined at that point but with a situation like this, then we say that discontinuities are removable. And when I say jump discontinuity, then the function is not continuous. Okay, and but the right hand limit and left hand limit are both finite, but the function is not continuous. So something like your function is continuous up to this point and the left hand limit exists, and we have some function like this to the right of that point, so that the right hand limit also exists, but these two limits are not the same. Then we say the function has a jump discontinuity. But if your function has a graph like then that is called infinite discontinuity. And in that case, in case of infinite discontinuity, we are not going to consider such infinite discontinuity case in our calculus class. Okay, that is a little bit beyond the scope of the calculus. So if your function is continuous or has some finitely many removable discontinuity or finitely many jump discontinuities, then your function is integrable. In other words, you can compute definite integral. And we will consider only such cases in our class. Okay? So we are not going to consider infinite discontinuity case. And if your function is integrable, meaning definite integral exists, then regarding this xi star, I can I can pinpoint that xi star on each interval. I mean, moments ago, if I have certain interval between xi minus 1 and xi, I told you that the definite integral is computed by considering some arbitrary point. And you evaluate your function at this arbitrary point. Now, if I know that, okay, so here in theorem 4, if I know that your function is integrable, then I can pinpoint my xi star to left endpoint or right endpoint or midpoint. Okay, I mean for the simplicity of the calculation. So if I know that my function is integrable, then the definite integral can be computed from the limit of a Riemann sum, and at this Riemann sum I'm just fixing my xi to be the one of the endpoints. Okay, so the left endpoint or the right endpoint, it doesn't matter, or even the midpoint is fine. So people usually choose one of these two endpoints for the simplification of the calculation. Okay. And let me skip this. You can read the slide. So let me go back to this. So as I said, if so this claim, the claim says, the theorem 4 says, if your f is integrable, meaning if I know that the definite integral exists. So if the definite integral of f exists, then you can choose xi minus 1 or xi as xi star. That's the meaning of this theorem 4. You can fix, okay, one of these two endpoints as your xi star. Now, regarding the proof, okay. Now, since, okay, even though I can prove the theorem, or we can easily prove the properties of this section, I'm not going to prove these properties. Okay, let me just show the properties directly, and then let me consider some examples later. Okay, I don't want to spend to prove these statements. So first, given this lower interval, lower limit, and upper limit. Okay, so when I initially derived this definite integral, we started with some interval from a to b. Okay, but in real application, okay, if you consider some engineering or economic problems, okay, we are not going to consider certain interval anymore, and we will just need to calculate a certain integration from a to b, and a doesn't have to be smaller than the b value. So okay, so given the integration from a to b or b to a, sometimes we need to switch these two limits, and mathematically, if you switch these two, you get one negation. So the integration of f from b to a will be the integration of f from a to b with a negative sign. Even though we can prove that, I'm okay. Let me just use it. Let me just take it as a fact. So, so in particular, if a and b are the same, then then the integration from a to b must be the same as the negative integration of a to a. And as I said, this integral is definite integral is a number. Only number which is the same as its negation will be 0. So if you integrate your function from a to a, you get 0. Okay, so integration of f from a to a, it will be 0. So if I consider the integration at a single point, it will be 0. And if I consider the constant, integrate constant c from a to b, what does that mean? That means I have a constant function c from a to b, and as I said, the integration represents the area of the region bounded by the graph and x-axis. And if I have a constant function, the area will be a rectangular shape. And the area of the rectangle can be easily obtained by multiplying the width and height. What is the width? Width is b minus a, and the height is c. So the area will be c times b minus a. So if I integrate constant c from a to b, you get c times b minus a. And if I integrate f of x plus gx, now if I have two functions, f of x and another function gx, when I add these two, you get this one. This is f plus g. Then the area between the graph of f plus g and the x-axis will be this area in purple. That will be the same as the area of this blue region plus the area of this red region. If you add these two, you get the purple one because this area in the red one is the same as here. Right? So that means the integration of f plus g will be the sum of the integration of f and the integration of g. In a similar way, if I multiply c to f, then its definite integral will be c times definite integral of f. And if I combine number 2 and number 3, you get this. So these are some simple properties. Okay, let us take a break for 15 minutes and let us resume at 10:30. Okay, Thank you for listening and see you in 15 minutes.